Welcome to Secure Software Development. We'll begin, as we always begin every class, by talking about magnetic door locks. In the picture on the right, you see a magnetic door lock. It consists of an electromagnet and a strike plate. When the electromagnet is engaged, it exerts a magnetic force on that strike plate. In this case, it's a grade 1 lock, and it exhibits about 1,650 pounds of force. That's a lot. If you want to open the door, you need to exert force equal to or greater than that, normal to the surface of that lock, to open the door. It's not impossible, it's just hard. One way you might do that, if you're a firefighter, you may have a halogen bar. A halogen bar is just a fancy pry bar, and you use the principle of moment or leverage to convert relatively few pounds of force at the end of that long stretch of the bar into 1,650 pounds of force at the end of that short tang, and that allows you to open the door. Simple. Another thing you might think about is the nature of the magnet itself. We know that magnetism decreases with as roughly the inverse cube of the distance. So we might plot that. Now, it's not exactly the inverse cube of the distance, right? There are some constants involved in that, and it's a little bit messy. The actual way in which this works depends upon the geometry of the magnet and the thing it's exerting the force on. In reality, magnetism behaves like other forces, the inverse square of the distance. However, magnets have two poles, and when you consider the contribution of each of the poles, and you do the math, you wind up with something along the order of an inverse cube. It's good enough. So, by knowing a few points along the curve, we can then generate the curve you see here. And this is roughly the curve for that class 1 lock we saw earlier. So, we can see that if we could open the door, it would be easy to open the door. It's a funny statement. But, it requires 1,650 pounds of force when the door is closed, when the distance between the magnet and the strike plate is 0. But that distance along the bottom, measured in inches, is pretty small. If I can get out to, let's say, 4/100ths of an inch, then look at that. The force has dropped all the way down to just 100 pounds to open the door. And it can go further down, right? So if I could get some separation between the magnet and the strike plate, then it would be easy for me to get the rest of the separation between the magnet and the strike plate and just open the door. Well, that feels like I'm begging the question, right? I'm telling you one way to open the door is to open the door a little. But bear with me. How could we do that? Well, we could put something between the strike plate and the magnet at some point, and that would make the door easier to open later on. Seems like that'd be the kind of thing you'd want to detect. And in fact, it can be. The locks could pass a small current through the strike plate, and that will tell it if the lock is truly closed, right? If the current is passing cleanly through the strike plate, then the strike plate and the magnetic face must be in contact. If it's not, there's separation, and so you could raise an alarm or do something else. So I would need a way to get some distance, but still be conductive. Wouldn't it be a lot of distance? What could I do? Well, one thing I might do is order conductive electrical tape. So they make this stuff. Typically they use it for absorbing electromagnetic radiation. So you would put it on electronics. You'll actually see it in consumer electronics put in various places to locally absorb EM radiation. It's cheap, and you can buy it yourself and have it lying around. So there it is. How thick is that tape? Well, it says it is 20 mil. What is 20 mil? Well, 20 mils is about 20/1000ths of an inch, or 2/100ths of an inch, or 0.02 inches. So if I slap a line of this tape on the door, then I've reduced the force necessary to open the door from 1,650 pounds all the way down to about 300 pounds, or a little less than 300 pounds. That may seem like a lot, but you would be surprised how much force is exerted when you take hold of the handle of the door and give it a good strong yank. Okay? You can exert quite a lot of force, more than you might think. But if that still seems like too much, if you use 2 layers of tape, it's still conductive, and now you get a separation that's double that. You go all the way out to the 0.04 I mentioned earlier, and now you're under 100 pounds of force. If that's still too much, right, 3 layers gives you 0.06, which puts you down around less than 50 pounds. Okay, but it's maybe a little more conspicuous. The tape is inconspicuous, it's gray, no one's going to look up and notice it. And all you need is an insider, a collaborator, or maybe you, if you happen to be there, to just sort of reach up and high-five the door lock on your way in or out with a nice piece of tape, and then you're ready to go back in later on, after hours, or when no one is watching. So, what can we learn from this little consideration? Well, one thing we can learn is that every system is vulnerable. The system we're talking about is an electromagnet. It's based on a simple physical principle, but it's vulnerable to this kind of attack. And it also tells us that we should consider using multiple independent approaches to secure critical assets. I might depend only on that lock. I might say that lock provides everything. That lock provides me with the ability to make the door difficult to open, because that's what locks do. They don't make a door impossible to open. They make a door difficult to open. If you want to make a door impossible to open, don't have a door. So locks just make a door difficult to open. And I can possibly use that little current I mentioned earlier, the little test to see if the magnet and the strike plate are together. I can use that to tell if the door is open or closed. Okay, great. I use that one system, but it can be defeated in that way, or in the way we just described, and that's bad. So maybe I use a second independent system, like a Hall effect sensor. Those are those little magnetic sensors that you see in pairs. Maybe you have them on your door at home or on your windows, so that when they move apart, they trigger an alarm. Little Hall effect sensors. I might use one of those. That's a separate independent system that can detect when the door is opened. And if the door is opened when it shouldn't be opened, I can raise an alarm. If your system connects to physical assets, like the door lock, you have to consider physical security aspects as well, right? And often, systems that are built for security will do one thing very well, but they might do poorly with other aspects of security, right? People tend to get in their lane, design a system that's secure in some way that they care about or understand, and possibly neglect other areas of security. You see that quite a bit. Lots of stories about that. Practice defensive programming. Right? Every system is vulnerable, so whenever you can, you should operate under the assumption that a separate system may have been compromised. Okay? You should validate and sanitize data from external systems and users. Okay? Your system obviously is super secure, completely correct, and absolutely impossible to be defeated. However, you don't live in your system doesn't operate in a vacuum, or else security would be meaningless. Your system interacts with other systems, and maybe those other systems get compromised, or they give you bad data, or they have errors. And so whenever it's possible or reasonable for you to do that, you have to say, hey, those other systems might have problems, and I should use potentially other information, or I should evaluate what they're telling me to try to determine if something is wrong. Practice defense in depth. We'll talk a little bit about defense in depth later on in the course. Upstream security can fail, or it could be subverted, right? Someone could have put that piece of conductive tape on the door lock, subverting that system. That's why it's important that you have additional security between the system and the user, between independent systems, and even at the API level. Right? Multiple layers of security constitute or can constitute defense in depth. Defense in depth relies on multiple independent systems and different approaches throughout the potential kill chain. We'll define kill chain as well later, but just think of it right now as what an attacker might do in order to defeat your security. You want to confront the attacker at every level of the system. Consider physical threats. Okay? Consider physical modifications and interventions to your system. Okay? Somebody might jimmy a lock. They might tamper with a sensor. They might unplug a cable. They might remove a piece of trim on your car in order to expose the CAN bus, plug into the CAN bus, and then use that to unlock the doors of your car or start your car. Document whenever your system depends on a physical sensor, some physical resource, or an actuator. It's important to put that in your security plan as well, and think about what that means for security. And consider whether you can detect tampering. You can't always detect tampering, but there are some clever ways to do tamper detection. Whole involved topic you can read up on. Tamper detection is surprisingly not used as often as you would think it is, right? We use it on medicine bottles. That's what that foil is for. That's what there's a whole bunch of different ways in which it's used, but it's seldom used as widely as you would think. It's just not present in a lot of systems, and it could be. Consider whether you can use a side channel to validate physical states. We'll talk about what a side channel is later in this lecture, and then maybe this statement will make more sense then. But basically, consider whether you can use other information from the world around you to say, yeah, the door really is open, or, yeah, the door really is closed. And consider how to handle loss of sensor input or loss of the control of an actuator. Everything eventually fails. We just live in an imperfect world. And while your code may be perfect, sensors break, actuators break, things fall apart. And you have to consider how to deal with those kinds of failures. Great. Let's talk about security in general. Security depends on a lot of different things, and some things we've talked about in that example are the environment, right? What if there's nobody around to see what you're up to? Maybe just grab the Halligan bar and pop the door open. You're done and you're in. Okay? If it's the middle of the day, there are cameras, the door's alarmed, maybe you don't want to do that. Maybe you do something else. Cooperation. An insider can place the tape for you, and then later on you can go and defeat the door. And adversarial capabilities. How hard is it to overcome security? And keep in mind that changes over time. Things get cheaper. Knowledge gets more widespread. Okay? Your little system guide is only available to people who've purchased your system. But eventually someone's going to scan it and stick it on the internet. Oh well, now it's out there. So be aware of that. Okay? How hard is it to overcome security? How much knowledge does the adversary have to have? How expensive is that conductive tape? Is it prohibitively expensive? It's not. It's really cheap. Okay, well then maybe I should design my system to take that into account. The point I'd like to make at the end of this is that lock I showed earlier is neither secure nor insecure. It's just what it is. It's an electromagnet. Security of that lock depends on the context. Okay? If I set it up wrong, then maybe an adversary can get access to the wires that feed power to it, snip the wires, and it doesn't matter anyway. The magnet's off. So it depends upon context, depends on how I set it up, it depends on how I use it, and it depends upon how it works in combination with other security elements to provide security. All right? The lock doesn't exist, again, in a vacuum. It's part of my entire security system for the building, which hopefully includes other things. Motion detectors, Hall effect sensors, other kinds of locks, so on and so forth. Okay? So, as a result, a system that includes that lock could be made more secure by that lock, or it could be made less secure, and it really depends upon the things we just discussed: the environment, the adversarial capabilities, and if there is an insider who can collaborate with somebody to overcome the security. Now we're going to see examples of all these things over the course of this semester, but a couple of these things are really worth emphasizing. The first one especially. Security issues often occur at interfaces. These are places where two components or two systems or the user and the system interact, where things come together. Okay? That's where security issues typically occur. And they occur for a variety of reasons, but often they occur because of a failure to consider all of the inputs at that interface. Someone discovers they can hand you a malformed packet and things break, or they discover that they can structure text in a certain way and you'll interpret it and things will break. Okay? Security issues can arise when you give information to an adversary. Any information given to an adversary will be used against you. So whatever information your system gives out, assume that your worst enemy is going to get that information, because that's how things work. Security issues can arise when there is tacit information in a system. What is tacit information? Explicit information is me telling you, hey, I'm going to the store. And you're like, okay, fine. Tacit information is my secret knowledge that I'm going to the store to buy you a birthday gift. Okay? So there's some tacit or hidden information there. When that sort of stuff is in your system, that can be okay. But it may also be the case that people don't realize that information is present in the system and it can be exploited, or people forget that it's there or forget why it's there, and they do other stuff. They build other parts of the system out and things go wrong. It's a little abstract right now, but we'll see some concrete examples of that later on. Security issues arise when there's an unenforced standard. So we say, hey, whenever anyone invokes a program on the system, the first argument to that program is going to be the name of the executable. Done. Easy. That's a standard, but is it an enforced standard? And if we can break the standard, what happens? We'll see examples of that, several examples of that actually, later on. And then finally, if you give people security access, some portion of them are going to give that access to others. They might do it unintentionally, they might do it intentionally. I have stories about that, but there you go. So think about your system as this bluish gray box, and think about the things that go in and the things that go out, right? The gazintas and the gazatas. So you might have a tacit assumption about data in your system. You might assume that when people enter information, the age will always be positive, the birthday will always be in the past, and the name won't contain any special characters, right? One of the things you might try is doing crazy stuff on those and just see what happens. Just see what happens. Weird stuff sometimes has happened. Another thing, the arrow going out the top, is giving information out to an adversary, right? Invalid ID tells me that that ID is not present in the system. If you're using emails as IDs, I can then find out if someone has an account on your system. Okay? Maybe that's fine and you don't care, or maybe that's not so fine. There are some, let's call them dating sites out in the world. And you might like to know, is this person I know, do they have an account on this dating site? So you go and you try to log in using their email address, and it says, you know, it doesn't say the email is invalid, it says invalid password. And then you try your own email address, and it says, you know, no such email found. And you realize, that confirms this person has an account on this system. Not great. My favorite message I got was trying to log into a system which told me my social security number was not found. And I was like, oh, wow, that's interesting. And so then you can dig around and you can find out which social security numbers, because there aren't a huge number of them, are present and which ones are not. It's fun stuff. You should also consider the full range of all the values. Is it okay to pass 0 or null or negative values, or values that overflow 32 or 64 bits? Sometimes, weirdly, I've seen, and we'll see over the course of this class, programs that take something in a, let's say, 2 to the 64th space, a 64-bit space, and then at some point start treating it as a 32-bit integer. They downgrade it to a 32-bit integer, and weird stuff can happen when you do that. So, you've been told a lot of things about how computers work. You've had classes that have explained computer architecture to you. You've had programming classes where they've told you things about how computers work. I'm here to tell you, we lied to you. We wanted to make it seem simpler than it is. We wanted to make you, encourage you and say, hey, it's not, this is just hard stuff, you'll figure it out. At the end of the day, it's all lies. The main one we tell you is that computers do exactly what you tell them, no more and no less, and oh my lord, that is completely a lie. Right? Computers are hellishly complex beasts. And you can try the thought experiment of saying, how complex is a computer? Okay? And you begin to think about the components and how they fit together and work together, and the buses work together, and there's protocols, and you think about the chip, and you begin to understand, as you begin to understand more and more of how it works, especially if you take the reverse engineering class I teach, you begin to realize this is unbelievably complex. However complex you think it is, it's more complex than that. Even modern microprocessors are actually little bags of other processors that run microcode to do various things. They're so complex, they need a computer to help them do their work. Computers will do work you didn't ask for. They will not do things you told them to do. And they will reorder the work schedule based on things that are out of your control. These three statements are all true. Okay, they're not maybe statements. Your computer will do these things. You have to be ready for that. So let's look at some code. So over on the right-hand side is some C code. I forget where I got this code from. I'm sorry. I've lost the provenance of some of the examples I have. But my examples are all from real systems. I like this one because it demonstrates a lot of, I'll just say, practices. So this is an unlock function. If you wonder what the uint64_t is up there, that comes out of the C standard integer library. On C++, that's C standard int. On C, it's standard int.h. Following that usual protocol of dropping the .h and adding a C in front of it to bring it in. And basically it lets you say precisely what the type of an integer is. So instead of saying int, which Lord knows what that could be anything, this says that's an unsigned 64-bit integer type. That's what unlock is going to return. It's going to return a hash. Okay, there are security weaknesses in this code. So let's take a look at what this code does. The first line goes and calls something that we can assume gets a password and hands it back to us as a character array. So we get a char star back that points to a password. We check to see if it's null, and if it's null, we return null. So we check to see if something went wrong, we didn't get a password for some reason, and if we didn't get a password for some reason, maybe there was no memory to be allocated or something else happened, we just return null. Good. Error checking is always appreciated. Then we define a hash as a 64-bit integer, and we go and invoke acquire lock. We pass it the password, and we pass it a pointer to our hash so that presumably acquire lock can fill in the hash value for us given the password. And we check the return value. And if the return value is not 0, we return a 0. Great, we're once again checking return values. Always advocate for that. That's great. So now we presumably have acquired a lock, whatever that means. And now we're going to do some work here. We go ahead and get the length of the password using strlen, and then we have a for loop. And that for loop uses an index, which runs from 0 up to len, and each time we do a pre-increment and bump the index. That's all good. That's how for loops work. We then overwrite the password at that offset with ff, and then overwrite it with 0. We are twice overwriting the password in memory to be sure that it's erased. It's no longer present. So if someone is sniffing through our memory, they won't see that password after this function is done. This is a good practice. As soon as you're done with a piece of secret information, erase. Don't just deallocate, but erase that information. Okay? Freeing it doesn't deallocate, doesn't erase it, it just deallocates it. We want to do both. So once we've done with that loop, we then free the password, and finally we return the hash back to the caller. So do any of you see problems with this code? Pause the video here, take a few minutes and look through it and see what you can find. I encourage you to take some time now and look through it. Okay, you ready? Let's go to the next slide. Look at that line right there. If the return value is, for some reason, non-zero, we return. Now, that's after the password is in memory. So someone entered a password, it's in memory, we passed it to acquire lock, and for some reason we didn't get a lock. We got some kind of an error back. We don't know what error we got back. We just got something that wasn't 0, which apparently indicates an error, and we returned 0. Now, one line of thinking would be, hey, that's okay, because acquiring the lock failed, which means that was probably an incorrect password, so it's okay to leave incorrect passwords in memory. But is it really okay? The password, if it's incorrect, might only be slightly incorrect, right? It might only be off by a small amount, and that dramatically reduces my search space for your password. Or it might be right, and the system could have been engineered to cause a failure because some resource wasn't available. Memory, for example, or some external database it needs, or something. So if I can cause a failure at this point, the password will still be in memory, and then I can go and look at it later on. And that happens. I think that's actually why I have this code. But also, wait a minute. We got the password, stored in password. We couldn't get the locks to be returned. We never freed the password. It's not that we didn't just overwrite it. That was bad. But we also didn't even free it, right? There's a memory leak. That's not good either. Memory leaks are bad. I mean, it's probably not going to be noticed. There's usually lots of memory, and entering 5 or 6 bad passwords isn't going to use up all available memory, but they're going to sit around in memory forever. And that makes the bug even worse, because they're just going to live there, allocated, so they won't get overwritten later. So as long as this thing is still running, those passwords are stuck in memory. Those possibly bad, possibly good passwords are just sitting in allocated but unlinked memory. And I can use some memory forensics tools to go and look around and poke around and see what's in there. That's bad. That's not good. I don't want that. All right, so those are some problems with this piece of code. So maybe I can trick the system into failing, even if you've entered the correct password. And it doesn't get overwritten. So how do we fix it? Well, one thing we might do is we have the return value right there after acquire lock. We don't have to act immediately. We can wait. So after we've acquired the lock, I go ahead and overwrite and then free the password, and then I check the return value and I return 0 if it's bad. So in this case, no matter what, I have gone ahead and overwritten and freed the password. It always happens. That's great. That's great. There's still some issues with this. I would like this chunk of code to execute atomically, meaning I don't want it to be split up. But that's a topic for another time. This is pretty solid. This is what I like to see. Much more secure, and the memory leak is gone. Much better. So let's compile it. So we compile the code, and then we run it through a disassembler. Now, I don't expect you all to know assembly. If you want to know assembly, take my reverse engineering class, and you'll be able to just read this like it's the Greek that it is. Unless you speak Greek, in which case it's going to be some other language. It'll never be super obvious. But one thing you can notice here is that the disassembler has helpfully put in some lines. So they're funny little colored ASCII art lines, but you can see one goes from up there at 11D2 and it goes all the way down to 1200. And there's another one that goes from 11EE and goes down to 1200. But all of the little lines go down. None of them go back up. Now, is that important? So take a few minutes to think about that. All of the control flow goes down, right? Either you're just doing instructions one after another and moving down that list, or you're making a jump and you're jumping further down the list. The one thing we can point out is that there's no loops going back up, which means there is no loop in there to erase the password. The password erasing loop is not here in this code. The compiler threw it away. And the compiler threw it away because it took a look at our code and it said, hey, let's go back to the code for a second. Password is a local variable to this function. It's not returned from this function, right? It's not used anywhere else. So all these things that are done to it after it was passed to acquire lock and then to Sterling, none of the rest of that stuff matters. It is what the compiler considers dead storage. And so any further access or modification or manipulation of it can be thrown away. And compilers are great. They're great at throwing stuff away. The primary focus of compilers is to throw stuff away. We have a fancy name for that. It's called optimization. And in this case, it's decided, hey, you told me to do that stuff, but you know, if I get rid of it, the program's faster, so I'm going to get rid of it. And that's what happens. Your whole password security stuff, it's gone. It still calls free, and you can see that happening on, I think, 11.7 up there. It's calling free to free the password, but the loop is gone. So how do we fix that? Well, the easy way to do it is to say, don't optimize this function. Just don't do it. Don't optimize it. Turn off optimization for this. And you can do that in GCC by adding an attribute up there at the top, where you specify, I want optimization level 0. Okay, that's easy. Another thing you might do is just turn it off for that particular loop. And I can do that by turning optimization off and then resetting the options down below it. And that will cause just that loop to not be optimized. And then one final way I can do it, there are a bunch of ways to do it, these are just some examples, is I could say, hey, password is a volatile variable. And I don't know if you all know enough C to know what volatile means. Volatile is a piece of storage that can change outside of the local program's control. So suppose I have a pointer to a memory mapped register that reads from a sensor. That's being changed in memory without my intervention. It's volatile, meaning that the compiler can't assume anything about its value staying stable. So in this case, we tell the compiler, you can't assume anything about password. Things could be happening with it. Someone else could be reading it. Someone else could be writing to it. You don't know. And so it then has to keep all this stuff in because it doesn't know if someone else is watching password. And you may wonder, what's up with all the char star casting in there? It's already a char star. That cast simply removes the volatile qualifier, right? Some things don't work with volatiles. For example, strlen. What's the strlen of truly a volatile pointer? I don't know, because it can change while I'm computing the string length. So I can't do that. I have to have something that's not volatile in order to compute that. So I have to drop the volatile qualifier off in order to do all the other things with it. Okay? And that presumes it's not really volatile. But this trick will cause the compiler to say, oh, I better leave it in because I'm scared of it. So, again, just to emphasize, computers will reorder your work. They will throw it away, and they will add to it. They will do all those things. Right? Sometimes for reasons that make no sense to you, but made good sense to a compiler writer. Compiler writers care about performance, not security or readability or any other illities we may think about. They care about performance, both the performance of the compiler and the performance of your code out the other side. Both of those are important. I don't want to wait a day for my stuff to compile, and once it's compiled, I want it to run fast. Great, but you have to be aware of the trade-offs that went into making that happen. Even modern assemblers, so you might think assembly is the lowest level of code, and so if I write assembly, I will get what I put in there. But even assemblers will optimize your code. There are tricks, especially on the Intel machines, where I can replace one instruction with another and maybe be more performant. So for example, instead of moving a 64-bit value into a 64-bit register, I can cheat and move a 32-bit value into a 32-bit register and have the same effect. That is called zero extended moves. Again, if you want to know the story, go take the other class. But yes, assemblers will modify your code as well, and sometimes you have to intervene so that they don't do that. The processor, and this is where you've really lost control, the processor itself is free to reorder your work, and it absolutely will do that. Discard it, and it does that, or add to it, and it does a lot of that. Processors spend a huge amount of time doing stuff you didn't ask them to do. sometimes stuff you don't want them to do. And we'll see some examples of vulnerabilities that arise from that. So, bottom line, the stuff's a mess. Computers are complex beasts. So, just to sum that up, the compiler, the processor, assembler, they can do stuff differently. And as long as the overall effect is expected to be the same, they can do anything. And you should be aware of that to some extent. Especially the notion of compiling away security. That is critical. Whenever the compiler or the processor changes the work schedule, you have the potential for a side channel vulnerability. Once they move stuff around, it's possible they move stuff around in a way that causes you to be vulnerable to an exploit. And we will see some of that. And modern compilers and processors always change the work schedule. Really beginning to sound like security is impossible, but bear with me. So let's stop now that we've gone through that, and let's think for a few minutes. What are some properties of a secure system? Okay, and that's kind of hard to answer, so let's back up a bit and say, what do people mean, or what do they think they mean when they say something is secure? And we'll talk about that in class, but here you can think about that for a few moments on your own, right? What do you mean when you say something is secure? Or when you say something is insecure? What do you mean, or what do you think you mean when you say that? And often it will have something to do with the notion of who is authorized to have information or perform an action. Right? The system will only do what it does for people who have some level of authorization. But what if there's collusion or an insider or someone is able to fake the authorization? What then? Well, we have to think about different aspects of confronting that. So give that some thought, and then we'll move on. So here are some questions. These are, I hope, relevant to this class. The first one is, what does it mean to write a secure program? What does that mean? What does it mean to say I wrote a secure program? Well, we're going to talk the rest of this class is going to be an attempt to answer that question. Is it possible to write a secure program? And would you know if you had? And presume for a moment that you write a secure program and you know you've written a secure program. The world does not stand still. Things evolve. People learn new things. New information comes to light. Right? Things that may have been secure on day 0 may be very insecure on day N. Security decays. So keep that in mind as well. Again, the rest of this class we're going to be beating on these questions. Let's take a detour for a moment and let's talk a little bit about systems theory. So general systems theory is this interdisciplinary study. You'll find a lot of it if you look at the field of cybernetics as a field, or if you go and look at some of the social sciences, or you look at biology, you'll find discussions of systems theory. This is a study of how complex organizations, and they could be companies, they could be economies, they could be multicellular organisms in a pond. They could be people and their various thoughts in their head. They could be collections of people together in sociology. How they function. Okay? And this is something that came up initially. The first thoughts were sort of before World War II, and then World War II emphasized a lot of systems thinking. And then after World War II, there was this explosion in trying to think about the world in terms of systems. And there are some of the maybe primary texts in this area. The first one, General Systems Theory, is the one that my advisor sent me off to read. Cybernetics, or control of communication in animal and machine. Von Neumann's theory of games and economic behavior. Shannon's mathematical theory of communication. These are all sort of foundational texts in this space. We're going to use a tiny bit of this. And we're only going to use this piece to try to say what we mean by a system and its environment, and try to put some discipline around that that we can use later on. So a system is a complex of interdependent components in mutual interaction. What does that mean? I don't know. It means there's some stuff that we call a system. Systems are defined more in an operational way than some pure deontological way. You'll say the system is that thing over there, and the environment is all the stuff around it. Okay? And that'll often be good enough. So the definition of environment that I actually like is the one here. The environment of a particular system is everything with which the given system communicates directly. So for a moment, let's say we don't know what a system is. A system is an unexamined thing. It's a black box. But the environment is everything that the system talks to, or that can talk to the system. Okay? So we're not including things that talk to a part of the environment, which then talk to the system. It's just the one hop. That stuff constitutes the environment. The environment and the system are going to influence each other, right? Unless there is no environment. Otherwise, they're going to influence each other, right? We can think of that as communication occurring between the system and the environment. There are parts of the system that are observable from the environment. We can think of them as outputs. And there are parts of the environment or conditions in the environment that are observable by the system, and we can think of those as inputs. So again, things that go in, stuff that comes out. And communication takes place over some collection of channels. We'll talk about channels more in a moment. The channels constitute an interface between the system and the environment. So one way to define a system is to say, here are the interfaces. And if I can tell you what all the different interfaces are, I have defined the system without having to tell you specifically what the system and the environment are. I've just told you, here are the interfaces, and that's good enough. Right? It's seldom productive to try to directly define the system. The system boundary is the collection of interfaces between the system and the environment. We define the boundary by listing the interfaces, and thus by extension, we define the system and the environment. So if you want to define a system, what I want is the definition of the system boundary. What does that look like? It looks like an enumeration of the interfaces between the system and the environment. Right? Could be APIs. It could be XML RPC calls. It could be it could be a tumbler lock. It could be a physical switch or a keypad or a camera or a motion sensor or a floodgate at a dam. Right? It could be the actuators for that. It could be any of these different things. Right? What are the interfaces? What are the things that allow the system and the environment to communicate, and what does that look like? So the interface is a method for transmitting information, like XML RPC or an API call. A channel is the physical mechanism that implements the interface. Okay? Channels will come up again. Channel comes from the Claude Shannon work I mentioned earlier in information theory. I have a communication channel. And the idea of the channel is useful when we want to talk about the capacity or the noise or the nature of communication at some low level, right? The channel might be, it could be more or less abstract. The channel might be, a fiber optic cable, and there's a capacity and there's a noise level in that. Or I might say the channel is an IPv6 tunnel between two machines, and there is some capacity to that channel. Okay? The interface is more useful to us typically in the computer science world because it lets us think about things at a higher level. Right? And it describes the interaction in this high level terms. But still, it has to get implemented some way at some lower level, and that lower level is the channel. We can think about functional and non-functional characteristics of a designed system. If it's something you encounter in nature, then I don't know that functional and non-functional necessarily have the same kind of meaning, right? But if we designed it, we intentionally designed it, we'll presumably know, oh, we intend these API calls, these things to be used in this way. Those are all the functional characteristics. But there are also non-functional aspects of a system that are the unavoidable consequence of the implementation of the functional aspects. And they can be properties of the system in a variety of ways. Heat, vibration, memory use, EM radiation, sound, time. All of these things are non-functional aspects of a system. Non-functional not in that they don't do anything, but that they're not part of the intended functional characteristics. All right? When I'm pushing keys on the keypad, they make a sound, and the sound is different for each of the keys. So if I'm close enough, I can record the sound and learn what a person's PIN number is, let's say. Maybe the different keys on the keypad result in different length of a connection. And so maybe there is in fact a high frequency noise generated by pushing a key on a keypad, and if I record it the right way, I can work out what the PIN number is. That can be done. And there's a whole set of things that the National Security Agency publishes about this. There's a Tempest stuff you can go and Google and look up. Computation involves work, physical work. Computation is a physical process, and even purely virtual systems, right? The metaverse, whatever you want to think about, that's still ultimately the result of some physical computation. Why am I going over all this? Because that is what a side channel is. A side channel is an observable, non-functional characteristic of a system. I can look at the system and I can see, in quotes, that it's producing heat, or it's vibrating in a certain way, or it's producing sound, or it's using more or less memory, or it's taking more or less time, or it's using more or less electrical power. That is a side channel. Channels communicate information, and from the information on that side channel, I can potentially infer something about the system that maybe I shouldn't be able to, or that I'm not intended to. It's an unintended channel of communication. And I can sometimes use that. So you can use side channels to break security in a number of ways. Otherwise, very secure systems can be broken in this way. There's a talk over on the right-hand side that you can watch, which describes the use of side channel information to break AES encryption. Very, very powerful, very solid encryption, but by using power analysis, they're able to break AES. Side channel information can be used to enhance security. We can do that by attestation. We can fingerprint devices and determine if it's a real device. We can possibly fingerprint the user and see if the way they're typing on the keyboard is indicative of their actual user. That's a side channel of information. And they can go both ways. We can potentially inject information into the system through a side channel, right? We can heat a system up, or we can cool it down, or we can shake it, or we can do other things to it and change the environment of it to change the way the system operates, maybe to our benefit. We'll see all this again later in class. All right. It's Tuesday, which means we have homework either due or assigned. There's nothing due, so there must be something to be assigned, and in fact there is. Our first homework is on understanding security. Pick a system. It can be a big system. It can be a medium system. It can be a tiny system. I don't care. Pick a system. It can be more or less complex. Just pick something that you're comfortable thinking about and talking about. I gave a lot of examples of various systems because I want you to think broadly about, at least for right now, the applicability of all these concepts. Right? Think about security of systems in a broad way. So, the national defense of a country, our entire Department of Defense and all the contractors and suppliers that work together with it to keep our country safe, yada, yada, yada. Regional hospital, city traffic system, an automobile, a family, the fare card system for a subway, various computer programs, an MMORPG, simpler stuff than that, whatever you like. Okay, think about that. And once you have a system in mind that you are willing to think about, and feel free to choose a different one if you don't like this as you go through this exercise, just pick one that you're comfortable going through this with. I want you to consider these different aspects of it, right? Hardware or biology, depending on the system you've chosen, maybe both. Software or automation is present in the system. Users or participants in that system. Policies and procedures around it. And the environment of the system. Think about those different aspects of it. Now, here's what I want you to write down and turn in. Give me an informal definition of your chosen system. It can be 92 Pontiac Fiero. Does Pontiac make a Fiero in 92? Probably not. 86 Pontiac Fiero. There you go. Define the system boundary by listing the interfaces that are needed to your subsequent answers. You don't have to tell me every single interface that's present, right? There may be a lot, and it may be that you don't know them all. Okay, it's difficult for you to enumerate them all. That's okay. Just tell me the ones that you'll need later on. And then pick 3 aspects of your system from the previous slide. Remember those? Hardware, biology, software, so on, automation. Pick 3 of those, and then for each one, give me a security property of the system. Tell me, here's something that I think is a security property of the system. And then explain to me how a weakness in that chosen aspect could be used to violate the security property. It's pretty abstract. But as an example, we might go all the way back to the door lock at the beginning and say, one property is that it takes 1,650 pounds of force to open the door. But you know what? If I put some tape up there, it now takes a lot less force to open that door. Right? That's a weakness in the hardware side of it that allows me to violate the property of requiring more force than I can expect an average human to exert. Now pick 2 aspects of the system from the previous slide and give me a security property and explain how a weakness in each of the 2 properties can be blended to violate your security property. So instead of just one aspect of it, I'm combining 2 weaknesses together. Okay? That may be a little tough. I'll leave you to stew on that a little bit and think about it, but blended threats are real. Identify a side channel for your chosen system, and then describe what information might be inferred from observing the side channel. Okay? One thing I could probably do is have a side channel that tells me whether or not the magnet is engaged. And right, I could do that, and I could have another side channel that lets me know if the door is, let's say, open, Or I could put a vibration sensor on the door, and if the door accelerates hard because someone has yanked it, I can trigger it that way and know that the door is doing something when it says it's closed. Okay, so think about that, those kinds of side channels, and don't use the door from the beginning of this and the examples I just gave. Pick your own system and go through this exercise. Write your answers out, preferably type them out and submit it as a PDF, and we'll all be happy and good. That's it.